Hello, this is Dr. K. Welcome to this week's module on design patterns. Design patterns are reusable ways of structuring your code so that it solves some common problem. These lectures are based on chapters 1 through 3 of the book Head First Design Patterns by Eric Freeman and Elizabeth Robson. The Head First series of books is an interesting series. They have a lot of pictures, diagrams, humor, fun facts, and bullet points. And from what people have told me, some people love this style of book and some people hate it. From my perspective, sometimes it works and sometimes it doesn't. For example, I'm not a big fan of Head First Java. Some of my students like it, but I find it hard to get into it. It feels like I'm just jumping around from one thing to another. On the other hand, Head First Design Patterns really works for me. This is one of my favorite books, and I think the simple, straightforward examples in here are one of the reasons for that. In any case, we're going to be looking at this book for the next two modules, so let's get started. The key thing to remember about software design in general, and design patterns in particular, is why we need good design. I mean, as long as the software works, as long as it does what it's supposed to do, why worry about how it's designed? Part of the answer is that it's just harder to build. And if you have a lot of poorly designed components, you're going to have problems integrating them. But the more difficult issue can be summed up in one word, and most of you probably know that the word I'm referring to is change. Software needs to change. It needs to be fixed due to bugs. It needs to be extended due to new features, and it needs to be adapted to new environments. Good design makes software more resilient to change, more able to handle changes without introducing new bugs. So if someone has a tried and true design pattern, it probably means that the design not only allows for the software to function as it should, but it also allows the software to be extended more easily in ways that we anticipate it may need to be extended in the future. In this chapter, we're going to look at a piece of software with a very straightforward design. Then we'll talk about potential problems that design might have. And finally, we'll look at another design that addresses some of those problems. We start with an application called SimuDuck. This is a duck pond simulation game in which a variety of duck species swim around in a pond and make quacking sounds. Okay, very simplistic application, but let's look at the initial design. Okay, here's the initial design of the SimuDuck application. Duck is an abstract class. In these slides, we will represent abstract classes and methods by underlining them. The class duck is abstract because it implements the quack method and the swim method, but it leaves the display method unimplemented. The implementations for methods in an abstract class can be thought of as default implementations. If most of the classes that inherit from the abstract class will have a particular implementation, then you may as well put that implementation in the abstract class so that you don't have to worry about duplicate code. Any subclass that needs to override the method can do so. For example, the quack method has a default implementation in the duck class. Mallard duck and redhead duck use this implementation. But rubber duck does not use the implementation. Since rubber ducks squeak instead of quack, the rubber duck class overrides the quack method so that the sound it makes is a squeak. Now let's talk about what needs to happen if we want to make an enhancement to our SimuDuck application. For example, what do we have to do if we want to add a fly behavior to this design? Take some time to think about how this diagram would change if we added a fly behavior. In fact, please pause the video and see if you can figure this out. Ready? I don't think this one is too difficult. Adding fly behavior to this design is a two-step process. First, you would add a fly method to the abstract duck class and give it a default implementation. Second, you would override the fly method in the rubber duck class since rubber ducks don't fly. The result would look something like this with the changes highlighted in red. Adding behavior to a duck object is one way to enhance this application. But there's another fairly obvious way to enhance the SimuDuck application. Can you think of what this is if I give you 5 seconds starting from now? All right. The other obvious way to enhance this application is to add a different kind of duck to your simulation. For example, suppose someone came up with the bright idea to add a decoy duck to the simulation. After all, you've already got the real ducks to satisfy the nature lovers, and you got the rubber ducks to satisfy, I don't know, mothers of young children. And now you want to add decoy ducks to satisfy the duck hunter demographic. In case you don't know, a decoy duck is a wooden duck that hunters use to attract real ducks. They put it in the water and hope that other ducks will come to it. So please pause the video again and decide how you would add a decoy duck to this design. Ready? I think this one is fairly obvious as well, but I want you to get in the habit of thinking these things through. To add a decoy duck, or any other kind of duck, you simply create a class that extends the abstract duck class. In this case, we're adding a class named decoy duck, and since it's a concrete class that extends an abstract class, it'll have to implement all the remaining abstract methods. In this case, there's only one, and that is display. But in addition to this, a decoy duck doesn't make a sound, so we have to override quack to do nothing. Likewise, we have to override the fly method to do nothing. And what we're going to end up with is something like this. And this is actually a benefit to this design. Adding a new kind of duck here does not modify existing code. As we're going to see later, this is a key design principle in object-oriented programming. Before going any further, let's take a look at this design. We've got an abstract class with a few default methods. If we want to add a behavior, we add a method with a default implementation to the abstract class, and then override it in subclasses when necessary. If we want to add another kind of duck, we simply add a new subclass, and we don't have to modify existing code. Now let's ask ourselves a few questions about this design. Now, I will eventually ask you to pause the video for this, but let's make sure we know what these assertions mean first. Is code or can code be duplicated across subclasses in this design? That one's pretty straightforward as far as the meaning goes. If we see duplicate code or the potential for duplicate code, we check this box. Runtime behavior changes are difficult to change. This means that if we have, say, a mallard duck, which can fly just fine, and we want to change that behavior at runtime, say, for example, the duck is captured or the duck becomes tired, can we modify the flying behavior of that particular mallard duck object so that it can no longer fly? The third assertion asks whether we can easily add a dance behavior to ducks in this design. The fourth assertion, like the second, is also asking something about the runtime behavior. If we have an arbitrary duck object, can a client of that object tell what its quack behavior will be, or what its swim behavior will be? The fifth assertion is asking if we can easily implement a behavior that would effectively combine two existing behaviors. And the final assertion is asking whether changes to some part of this code might unintentionally affect other duck objects. Okay, now that you know what these assertions mean, go ahead and pause the video and try to decide which of them apply to our current design. Ready? Let's take them one at a time. Can code be duplicated across subclasses? The answer is yes. In fact, there's already code duplicated across subclasses, and that is the rubber duck fly method and the decoy duck fly method. Both implementations override the default duck implementation by making the ducks do nothing when the fly method is called. Because the overriding code for both kinds of ducks does nothing, it may not result in a lot of duplicate code, but it's still considered duplicate code. What about the second assertion? Are runtime behavior changes difficult? The answer here is also yes. Inheritance relationships are fixed at compile time. Once you decide how a mallard duck is going to behave, that behavior cannot be modified at runtime without essentially hacking the client code. So if you want a mallard duck object to be able to fly sometimes and not fly at other times, you're better off using a different design. Next, we can't make ducks dance. Well, that is not true. All we have to do is to add a dance method to our abstract class. Next, is it hard for the client of an arbitrary duck object to know how that duck behaves? Actually, it is. You can do it, but it's not as easy to do as it would be with another design. Here's how you would do it in this case. You would have to check the actual type of the duck object with, say, the instance of operator in Java. That would give you the subclass of duck that you were dealing with. As long as you know what the behavior is for that kind of duck, you know how the duck object will behave. So it's possible, but as we will see, it's a lot easier to do in another design. Next, can we make ducks fly and quack at the same time? Well, why not? Just add another method, fly and quack, and either call through to the methods fly and quack or write custom code for the fly and quack method. Finally, can changes unintentionally affect other ducks? The answer here is a definite yes. This can happen if you add a new behavior in your abstract duck class and give it a default implementation. If you forget to override that behavior in duck subclasses where the behavior is not appropriate, then you have a problem. So let's go back to our initial design with the fly behavior and the decoy duck added. And let's look at one particular issue. There are three methods here that override the abstract duck class to do nothing. One is quack in decoy duck and fly in both rubber duck and decoy duck. This seems odd. I mean, if these methods are not going to be implemented in certain subclasses, maybe it's better if these methods were optional in some sense. In fact, you can do that by removing the methods from the abstract duck class and giving them their own interface. In this alternative design, we have a flyable interface containing the method signature for fly and a quackable interface containing the method signature for quack. The mallard duck class and the redhead duck class implement the flyable interface, and the mallard, redhead, and rubber duck classes implement the quackable interface. Rubber duck does not implement flyable, and decoy duck does not implement either interface. Okay, so one problem solved. You don't need rubber duck and decoy duck to override methods to do nothing. Unfortunately, you just introduced another problem. If it's not obvious to you, please pause the video one more time and see if you can determine a serious problem with this design. I'll give you a hint. This was a problem with our original design also, but it's arguably more serious in this design. Ready? First, I'll tell you something that is no longer a problem. When you add a new behavior in this design, you will not inadvertently affect the behavior of other ducks. This is because you will, presumably, add an interface here instead of a method with a default implementation. So you won't be affecting behaviors of other ducks until you implement those behaviors in the concrete classes. Runtime behavior changes are still difficult, and it's still hard to gain knowledge of duck behaviors. However, I think the most obvious problem is that you now have duplicate code. And it's not duplicate code that does nothing. It's duplicate code that does something. The fly method and the quack method in mallard duck and redhead duck, and for that matter, any other duck that behaves like a normal duck, will have to implement the exact same code in the exact same way. And the code would have to be kept in sync while the software is maintained. Needless to say, this is not an acceptable option.